enjoy the weather. That will make me less nervous. Great. All right, I'm going to switch a little bit gear and talk about noise parameter characterization and a particular methodology that we developed at NRL that has been validated through the effort, a team effort really with the University of Messina. Let's see if I can do that. Yeah, so this is the overview. I'll just introduce the team and tell you what the project goal is, give you the approach that we use to validate the new technique, show you some measurement, and then the conclusion and hopefully what we're trying to do next. NRL is located in Washington, D.C. University of Messina is in southern Italy. Never been there. It's a random occurrence that I've been working with an Italian university, although I am from Italy originally. The team goal is really to provide an independent confirmation of the noise parameter extraction versus size, which is a procedure that, as I mentioned, has been developed at NRL and has been proven earlier before, but has not been compared to a standard method to extracting noise parameters. So this has really been the goal of this effort. We had available, or I should say, the University of Messina had a bunch of devices available already from TriQuint, GaAs pHEMT, and I'm showing here just a sample of what we measured. We have much more data available. The wafer also came with some calibration structure that we used for the characterization of the devices. So I'm going to go through some quick description of what the university has been doing, and this is really, I would say, textbook stuff. I'm not trying to take anything away from them, but is the lane approach that they implemented to extract the noise parameters from the devices available. This is the setup, basically, that they used. I want to point out the wafer probe station that they used, which is basically in common with our approach. And then what is really different at this point is the tuner, because they used a tuner to make the measurement on each device, which is a time-consuming process. If you have the experience of doing it, it's really something that takes time. You have to characterize it, safety data, and then reuse the data. So it's not an easy process. It may be straightforward, but it takes time. The other one thing very important that they really did, and they're good at, I would say, is to extract circuit that models the behavior of the device. The agreement, in order to validate our procedure, the agreement was to make all the measurements at a constant VDS and JDS, constant current density point for the device. And that is what allows us to make the comparison at the end of the day, as I hope I'll show you through these slides. What they also did is to, the paper has some more information, but is to determine what the values of the extrinsic circuit components are, and then also to determine the values of the intrinsic circuits, the components of the intrinsic circuits. In this process, you can also, once you have the scattering parameters, the noise figure data, you can basically apply the lane procedure, get the noise parameters. Eventually, you get to the point where you can determine the noise temperature and the noise temperature of RGS and the noise temperature, equivalent noise temperature of RDS. And this is because the, I can say, well-known Pospieszalski noise model has been used. Because of that approach, basically, we already know that RGD has an equivalent temperature equal to the room temperature. So if you want 300, 290 degrees to be formal, but that is the value of the temperature associated with that resistor. And then they could extract, basically, what is important here is the TDS of that resistor. And they did that, but they didn't disclose, of course, the result, because that is really the objective of the comparison and the validation of our two approaches. So then, after they did that for much more than 7 devices, so for every device extracting the component values, noise parameters, noise temperatures, do the noise characterization, they shipped out the devices to DC, and we have a similar setup. We have a PNAX and a wafer probe that was in use. We have more than one, although from the picture I have to say that their lab looks much tidier than ours, but that's just my impression. And then we do basically the same type of measurement. The main difference is that we no longer need the tuner. And I don't go into the details of the procedure, but basically we don't use the tuner because the knob, as I like to say, the knob that we are changing, instead of being the gamma S, basically, through the tuner is the size. And by changing the size, we have that variation that we can detect through the measurements. But we don't need, basically, we don't need any additional instruments that, like the tuner, that provides a bottleneck to frequency, range, more complexity, time consuming. You add whatever you want to that list. But all you need to do is to land the probes on the device the same way you do when you do the S parameter measurement. And with the equipment that is available now, basically press a different button and do the noise characterization, noise figure measurement. Maybe I'm being a bit optimistic, but that's the idea. So then, once we have collected the data, we use the same topology, the same architecture of, not architecture, I'm missing the words now, but the same circuit there. At the same, this is also important, at the same bias point. It has to be the same VDS and same current density in order to make this type of measurement and comparison. So having done that, we go on and basically we take out the contribution of the extrinsic element, and then we make the intrinsic component, the intrinsic circuit, scalable versus the gate length. After having done that, then we can do an analytical least square method fit to the data that we have, and that is what has been previously published and described. There's a patent assigned to NRL on this subject. And basically we get the noise temperature. I guess I have to be, how can I say, scientifically correct. I am, as you have noticed, I'm mixing up a little bit. I'm not precise on the terminology when I say noise parameters, but I refer to noise temperature. There are actually two different things, if you will. Here, I'm really making the assumption that this model is scalable, and I'm using the Pospieszalski model that has certain properties of uncorrelated noise temperature. It takes this contribution out, so it's unilateral. That is sort of true and overcome by this method, meaning you can actually extract this number 2 through the math that is developed, that has been developed. The other thing is I want to point out, because it was a very clever comment from one of the reviewers, that we don't make a distinction here of how many fingers you have versus the length of, not length, the width of your gate, meaning the 2 by, actually no, it's 4 by 25 or 2 by 50 device. In this, the way we develop the math is the same device. You don't capture the details that you may capture through a different type of model. Having said that, I think the step that you have to take is to basically refine the math behind and then do the same extraction. At the end of the day, you always want to end up with a LSM type of approach against the measured data. So I want to show what we measured, just a sample of devices going from small to big. Let's start from here. This is the bias. The VDS is common, is not reported there, but the blue trace is the current, the IDS current versus width. So it increases as expected proportionally. That's what we did, make sure that that happened. And the current density is this jittery trace, but it's all, if you look at the numbers there, is 210, 199, 92. So it's 200 milliamp per millimeter. And that's what we wanted to do. The noise, well, let's do the scattering parameters are shown here. You see a little bit of difference between the green trace that looks much better on my screen and the blue trace. The reason is that distance is distance. There was a little bit of miscommunication, I guess, and in the extraction, there was a problem with the reference plane, which was explained then by the university through some simulation, and it's also explained in this paper that they published, we published recently, just before ARFTG. But the noise figure measurement F50 here, you see it's very similar despite having been executed in 2 different places at different times. And this is really independent of whatever very low loss components you may have, right? Because it's essentially a power measurement independent of the reactances that may be there. So as I mentioned, you need to make the model scalable, and that's what we did on this side of the Atlantic. And you can, we did everything within ADS, as you can tell from the plot. Within the simulator of your choice, you can do it. We did it in this one. We're familiar with ADS. So you can extract basically the average value automatically out of the measurement of the 1, 2, 3, 4, 5, 6, 7 devices, as I mentioned before. This is just the sample subset that we used for publication purposes, really. And these are the values of the capacitors, just in the intrinsic. I'm talking about the intrinsic circuit, of course. Resistances, and this is the GM, and this is the tau, and then there are 8 components. So this spot was filled out by the GM, which is reported there just for being complete. And then once you have all this data, you can apply the procedure, you can extract the values of the 2 temperatures, and this is what you get. So for every frequency, basically you can use the simulator to extract the value of the temperature. And then these are the crosses here is the result of that, and then you take an average, which is the black line, and that's the value of the, in this case, extracted TDS. Similar for TGS. So these are the numbers that we say through our procedure we obtain those numbers. How do they compare? The comparison is in this table. It's a simple comparison to make. So the University of Messina extracted basically 4,700 or 4,800 Kelvin for TDS. And as I mentioned before, they assign a priori as the post-Wiesalski model and all the publication, hundreds of publications that came after that, basically tells you that the TGS is room temperature. And so they use 290. The numbers that we extracted are these ones, 4,900 and 330. And given that this is sort of arbitrary number, you could put 300 there and nobody complains. So you see that the difference is very minimal, and particularly for TDS, because TDS is in the 1,000, and the difference is really, may I say the joke, in the noise. Then you take those numbers, those temperatures, you put them in your model, in your simulator, run for every device, run the simulation, and you get these results for noise parameters. So one is the F-mean, Rn, gamma S opt, amplitude and phase, and that's the complex number that you get over frequency. And this is for the small device, the 2x50, 4x50, what is it, 4 by, I can't read now, I'm sorry, 6x50 and 10 by 60. So you'll be the judge whether it's a good approximation or not. But the point is that you can, you don't have to sit at your computer and try it out with, you know, if it's a good day or a bad day, you may get different numbers. This is an analytical approach. Given a set of data that you measure, these are the numbers that you get. So, my conclusions. We used the same DUTs. We had comparable results with 2 very different techniques. We shared the devices, and this is really my accomplishment, that the size-based technique is validated against, independently validated against data collected in a completely different way. It is a path of automation for the reason I try to explain during my talk. There's no, you don't need equipment. I've been looking at this effort from the standpoint of a fab that gets wafers out and they can measure and they can test them, collect data. They can do that on PCM during the process, but that's the point. You don't want to have any roadblock to make the measurement of the noise parameter more difficult than what it should be. So this approach is, in my view, potentially a way to automate that, similarly to what PNA does with the S parameters. You can, with modern instruments, you can really think you could make a software algorithm in the instrument and then have somebody click the button once the probes have been landed on the device. And the future work is really, I see this in diverging in two different directions. One is to extend the validation in frequency, but also, I didn't put it there, also in temperature. I don't see any reason why this cannot work if you lower the temperature, or you increase it if you want. If you lower the temperature of your device to 77 Kelvin, I really don't see why this approach cannot work. I think it's going to work. As long as, unless we sit down and develop the new math behind it, but as long as you can use FETs, you can use the Pospieszalski noise model, and we know that that is possible, then you can just basically apply what is available right now and go in this direction. We have a patent. The other direction is to remove the model dependency, and that is also quite interesting because, well, gallium nitride devices are very important, but I've been working in the recent past with SiGe devices. Those are HBTs, and despite publication and so on, I noticed that people that come from the silicon world often don't even know who Pospieszalski is or did. Shouldn't there be a gamma somewhere in your expression? So they're used to MOS devices, and they have a completely different approach. So removing the model dependency from the approach, it's possible. We basically have a very clear idea of what to do, and we have also filed a new patent, which eventually the PTO will tell us what they think. But this is one direction that I'm also interested in, because it's slightly more complicated than what you may think looking at what has been developed so far. But thank you for your attention. I believe we used, Jason, my colleague, used both of them. The data that we collected, I think it was through the 3ATC, I can't remember whatever it's called, the noise source, on a different equipment that we already had in place. As I mentioned, our lab is more, it's not as tidy as it shows in the pictures, but I believe we did both of them.
Okay. I would just like, you are using PNAX, it actually does source fault in the noise spectrum measurement. But it's an electronic tuner, it's very fast, it's not like a mechanical tuner.
That's true. You also have the right, if I'm not mistaken, you have to have the right personality assigned to that PNAX to do that. And the one that, oh, sorry. the PNA X that we have as the noise personality, or whatever it's called. Yes, with the different receiver. And I'm not completely sure, to be honest, on what the university did. They told us what type of PNA they used. I don't know, I don't remember if they mentioned whether they used the personality or not. But that is true. What I'm interested in out of the measurement is really the number that I get out of the instrument, right? And maybe I shouldn't say that this here, but at the end of the day, I'm not looking for a precise measurement. I'm looking for the data that can extract this number, this magic number that I can put in a simulator and validate the approach across the devices. So I don't know if I make sense with my answer to your, or I respond to your question with my answer. I'm not sure where you were going with the pointing out that how the PNA makes the measurement, but
I don't. A related question, because the PNA has two modes. One is a scalar noise figure measurement, which would take whatever raw source match is provided to the device, and that's what noise it's measuring and getting a noise figure from. It also has a vector corrected noise figure, which is, as he mentioned, using its internal tuner to create a few states and get a better 50 ohm noise figure. Can you say which one, and if you were using the scalar, did you then find what the source termination was and use that in your map?
so when we used the PNAX, we went through the whole procedure. So it was the vector measurement. Yes, but we did not go and look for what value of GaAs was used, if that is what you're.
Well, that would matter in the scalar. In the vector, you've effectively made it perfect 50 ohm.
That's the point, right? So there I can use 50 ohm, and that's. I mean, the math is developed in such a way that if it doesn't matter if it's 50 ohm or 51 or whatever. You would have to know what it was. Yes. So as you can tell, I'm not a measurement guy. I don't know what I am, basically. But I follow the procedure. I get the numbers, and then I apply them. In the noise parameter measurements, my experience has been that is always very, how can I say, it's not a precise measurement you have. That's my limitation. Sorry if I said that.
You say noise measurements are noisy?
Maybe that's what I meant.